So the the first speaker of the session is Professor Chris Lambie-Hanson from Virginia Commonwealth University. And the title of talk is Strongly Unbounded Colorings. So please go ahead.
Great, thank you. I'd like to thank the organizers for the invitation. It's an honor to be a part of this conference. So I'm talking today about some joint work with Asaf Renote about strongly unbounded colorings. But before we get into the sort of meat of the talk, I want to talk about the problem that sort of initiated the whole project. And this is a problem that relates to productivity of chain conditions, and in particular, productivity of the Trinaster property. So Trinaster is apparently the name of a line of decorative rocks that IKEA sells. But it's also this Polish mathematician. And it describes a strong chain condition. So probably most of you have seen this, but let's review the definition. So throughout this talk, kappa will denote some arbitrary, irregular, uncountable cardinal. Remember, we say that a poset P is kappa Trinaster if whenever we have a subset of P of size kappa, call it A, we can thin A out to a subset B, still of size kappa, such that B consists of pairwise compatible conditions. Right? So this is clearly a strengthening of the kappa CC. And one of the reasons that it's quite useful is that unlike the kappa CC, which in general is not productive, the kappa Trinaster property is always productive, right? So in other words, if P and Q are both kappa Trinaster, then their product P times Q is also kappa Trinaster. And in general, this will fail for kappa CC, right? For instance, kappa Suslin tree. Or for many kappa, there are just CFC examples of kappa CC posets whose squares are not kappa CC. All right, so we might also ask for more though. So this tells us that any product of finitely many kappa Trinaster posets is kappa Trinaster. But what about infinite products? So we might ask for stronger productivity. So for an infinite cardinal theta, let's say that the kappa Trinaster property is theta productive if whenever we have theta many kappa Trinaster posets, pi for I less than theta, their full support product is also kappa Trinaster. So we might ask, for what cardinals theta and kappa is the kappa Trinaster property theta productive? So as a first step here, it's not hard to show. It's basically just a consequence of the Ramsey theorem holding in kappa, that if kappa is weakly compact, then the kappa Trinaster property is theta productive for every theta less than kappa. Right? But this does not characterize weak compactness. So there's a theorem of Cox and Luca from 2017. They need to assume the consistency of a weakly compact cardinal. But assuming this, there's a forcing extension in which there's an inaccessible cardinal kappa. Kappa is not weakly compact, but the kappa Trinaster property is still less than kappa productive. There's a partial converse, though. Myself and Philip Luca proved a year later that if the kappa Trinaster property is even L of 0 productive, then kappa must be weakly compact in L. Right? In particular, from square parentheses kappa, you can cook up a poset that's kappa Trinaster whose L of 0th power is not kappa CC. Right? So the weakly compact cardinal here in this theorem of Cox-Luca was necessary consistency-wise. So we have an equiconsistency here, but not an equivalence. So these results, though, left open a natural question. In this theorem of Cox and Luca, kappa remains inaccessible, right? But what's the situation for accessible cardinals? So is it consistent that the kappa Trinaster property can be infinitely productive, L of 0 productive, for some smaller cardinal, like L 2 or L omega plus 1? Right? And the answer turned out to be no. So Asaf and I proved at the sort of start of this project that, in fact, if kappa is any successor cardinal, Then there's a Kappa-Trinaster poset P, such that P to the L of 0 is not Kappa-Trinaster, it's not even Kappa-CC. Right? So this answers this question. The proof of this theorem, and I'm going to stretch it soon, ended up being not particularly difficult. It involves colorings from pairs of kappa to omega that satisfy certain strong unboundedness properties. And this initiated for us a sort of systematic study of these colorings, their variations, and some of their applications that I think has led to some interesting places. So today I'm going to sort of survey some of the results, or not all of them, that we've obtained in this sort of investigation. All right. So these are the 3 papers that comprise this project. The first 2 are published already, and the third is in preparation now and will hopefully be available soon. All right. So let's start the talk proper now by introducing sort of the main object of study, which are these strongly unbounded colorings. All right. And so these strongly unbounded colorings are going to be sort of codified by a parameterized definition that has 4 parameters. 2 of them are more important sort of for basic understanding than others, and that's the first and third, but we'll get to them in just a second. Okay. So what does this principle assert? The principle U kappa mu theta chi asserts the existence of a coloring C from pairs of kappa to theta with certain properties. All right. So the first parameter here is the sort of domain of the function, or the pairs of that ordinal domain. The third is the codomain. So before I state the properties, I want to sort of think about what they should be intuitively. U here stands for unbounded. So the properties that this coloring has are going to be, it's a strongly unbounded coloring. And what do we want that to mean? Okay, well, as a first approximation, we might just mean that, okay, the image of kappa squared is unbounded in theta. Okay, but, you know, there's always a coloring like this if kappa is greater than theta. This is too weak. We want a sort of more robust notion of unboundedness. And if you've been about this for a little bit, a natural candidate for this would be, okay, of course we want the range of C to be unbounded in theta, but maybe we want the image of every unbounded subset of kappa to be unbounded in theta, right? So maybe we want for all unbounded A subset of kappa, the image of A squared is unbounded in theta. Okay, and now we get a really interesting property. This turns out to be a specific instance of this U property, as we'll see in just a minute. This is U kappa to theta 2. Okay. For a lot of applications, though, we want something a little bit stronger even than this. So what do we really want? Let's do the actual definition now. So U kappa mu theta chi says there is some coloring, some strongly unbounded coloring C from pairs of kappa to theta, such that if you hand me any family of kappa many pairwise disjoint sets, all of some fixed size less than the 4th parameter chi, and you hand me any fixed color I less than theta, I can find a subfamily B of A such that whenever I take 2 different elements from that subfamily, the image of the product of those elements is, greater than I. So let me try to draw a little picture here. Let's say that here is my family A, right? And because it consists of small sets and they're pairwise disjoint, I'm thinned out so they really are ordered like this, right? And let's say I also have some fixed I less than theta. What this is saying is I can find mu many of the sets, maybe, these are in my family B. Such that whenever I take elements from different of these sets in B, C alpha beta is going to be greater than I. Okay. So what the second and fourth parameters are telling you are, the fourth parameter is telling you how large you can take these elements of A. And the second is telling you how large of a sort of homogeneous set you can get. Homogeneous here doesn't mean takes the same value, it means takes value above the fixed color you've given me, right? And in a lot of applications, this mu will actually be kappa. So this beta can have full size in A. So this principle can be seen as asserting a very strong failure of Ramsey's theorem at kappa, right? If we really had Ramsey's theorem at kappa, then any coloring like this would be constant on a large set, right? And this would obviously not be unbounded. Okay. Also note that there's some monotonicity in the second and fourth coordinates. If mu prime is less than or equal to mu and chi prime is less than or equal to chi, then mu u kappa mu theta chi implies u kappa mu prime theta chi prime. Decreasing the second and fourth parameters makes it easier. But notice that there's no such obvious monotonicity in the third coordinate, right? Because having a coloring that's unbounded into, say, omega 1 doesn't obviously give you one that's unbounded into omega, because there's this mismatch of cofinalities. All right. So how does this give us a failure of infinite productivity of the Trinaster property? This might help to sort of illuminate the definition on the previous slide. So this is the key lemma that sort of started this whole project. Suppose we have infinite regular cardinals, theta less than or equal to chi less than kappa. If you want to, for now, you can think of theta and chi as both being Aleph 0. That's the most important case. Suppose kappa is less than chi inaccessible, meaning for every lambda less than kappa, every nu less than chi, lambda to nu is less than kappa. And suppose this property u kappa kappa theta chi holds. And there's a poset P such that, okay, P is closed, it's chi-directed closed. That's what this fourth parameter is doing. But more importantly, not only is P kappa Trinaster, but P to the tau is kappa Trinaster for all tau less than theta. Okay, so all the powers of P are Trinaster all the way up to theta. But at theta, P to the theta fails to even be kappa CC. All right, so I want to sketch a proof of this. So let C be a witness to this property, u kappa kappa theta chi. Right? And for all I less than theta, I'm going to let pi be the poset whose conditions are all subsets of kappa of size less than chi, such that the minimum of the image of x squared under C is greater than I. So the pair of any two ordinals that I take from X, they get mapped to a color greater than I by C, right? So these are sort of the greater than I homogeneous subsets of kappa of size less than chi. Right? And the ordering is just reverse inclusion. Right? Now let P just be the lottery sum of all of these PIs. I claim that this works. All right, I'm going to sketch a couple of the things to check. I'm going to check, all right, I'm not going to prove that P to the tau is kappa Trinaster for all tau less than theta. Let's see why P is kappa Trinaster. All right, so suppose that we have x eta less than kappa and P. All right, so without loss of generality, what can we assume? Well, P was this lottery sum of these theta many PIs. we can assume all these x etas are in the same pi. So there is some I less than theta, such that for all eta less than kappa, x eta is in pi. Okay. We can also assume by this assumption of inaccessibility that these x etas form a delta system. With root, let's say, r. Right. So what do we have here? We have this root r, and then we have, say, an x eta 1, x eta 2 above it, or like this. Okay, now what we're going to do now is apply the fact that this C witnesses this U property not to the x etas, but to the x eta minus r's. So apply the fact that C witnesses U kappa kappa theta chi to the family A, which is x eta minus r for eta less than kappa. And what does this give us? This gives us an unbounded B subset of kappa such that for all eta 0 less than eta 1 in B, the min of C x eta 0 minus r times x eta 1 minus r is above I. Right? But now this is exactly what we need to ensure that x eta 0 union x eta 1 is a legitimate condition in our forcing poset. So then for all eta 0 less than eta 1 in B, x eta 0 union x eta 1 is in P, and extends both x eta 0 and x eta 1, right? The only way this could fail to be in P is if there's a pair of ordinals in this union such that C of that pair gets color less than or equal to I, right? But any such pair, okay, there are three possibilities. Either both of them are in x eta 0. X eta 0 is a condition, so we're done. Or both of them are in x eta 1. X eta 1 is also a condition, so we're done. Only non-trivial case, we have one ordinal from x eta 0, one from x eta 1. Neither is in the other. But then they come from these x eta 0 minus r and x eta 1 minus r, and we thinned out so that C takes values greater than I there. Right. So we found this large size kappa subfamily of our family consisting of pairwise compatible conditions, and we're done. Okay. Good. So that's why P is kappa Trinaster. I used all of the room here. Let me erase this last bit. Or I'll erase this top bit to show why P to the theta is not kappa CC. Okay. So we have to define an anti-chain of size kappa. For alpha less than kappa, define a function f in P to the theta by letting f of I be in pi, and f of I just be the singleton alpha, right? Singletons are always conditions, but I claim that this will be f alpha. I claim that for any alpha less than beta, f alpha and f beta are incompatible. Because if alpha less than beta, then singleton alpha and singleton beta are incompatible in P sub C alpha beta, right? Because alpha beta is not a condition in P sub C alpha beta, right? And so F alpha and F beta are incompatible in this power because they're incompatible in their C alpha beta coordinate. All right. Okay, so this shows that we have this counterexample to productivity of the Trappist-Naster from this coloring. Right. Now, when does this coloring property U kappa kappa theta chi hold? Well, this principle had actually already been implicit in a variety of previous work, especially a lot of work of Todorcevich. In his work on the Waxon ordinals, he proved the following theorem, not phrased in this way, but it was exactly this. This principle holds in every successor cardinal in the way we wanted to. So for every infinite cardinal lambda, U lambda plus aleph 0 profinality lambda actually holds. It turns out you can do this by doing Waxon ordinals on C sequence of length lambda plus and looking at the number of steps function. Right. But now this gives us precisely the instance of U that we need for this corollary, given the last lemma we had, right? For every successor cardinal kappa, the Trappist-Naster property fails to be aleph 0 productive, right? This aleph 0 is precisely this parameter, right? But this got us interested in other instances of this property and when they hold or fail, what we can say about that. So we sort of started to investigate when this property provably holds in ZFC. All right. So before studying some of our results, I want to give another definition. If I have a coloring C from pairs of kappa to theta, and I fix some ordinal beta less than kappa and some color I less than theta, I want to let D C less than or equal to I of beta just be the set of alpha less than beta such that C alpha beta is less than or equal to I. Right? This is a sort of standard way of turning a coloring into a matrix of sets. Right? And we say that C is closed if each of these sets is a closed subset of beta. It turns out that when we construct these colorings, it's nice to have closed colorings, and the ones that we naturally construct end up being closed anyway. All right. So in the first paper of this series, most of it was dedicated to, or a lot of it was dedicated to proving that in a lot of instances, this principle just holds in ZFC. All right. So suppose that we have cardinals theta chi less than kappa, all regular cardinals. Any one of the following statements entails that this property U kappa kappa theta chi holds, right? And therefore entails some failure of productivity of the Trappist-Naster property. First of all, if we have any non-reflecting stationary subset of kappa concentrated on ordinals of profinality at least chi. Right, so any failure of stationary reflection gives us non-trivial instances of this U property. Okay, 2, this is just a special case of 1. At the successor of a regular cardinal, every instance of this U property just holds because we have this non-reflecting stationary set consisting of ordinals of profinality lambda. All right, so there's not a whole lot to prove at successors of regular cardinals. This principle just always holds, which is nice. If kappa is lambda plus and the profinality of lambda is theta, then it also holds. So even at successors of singulars, it always holds as long as you want your codomain of your function to be the profinality of this predecessor. if square of kappa holds, then again, any reasonable instance of this property holds. In fact, as we'll see later, something a lot stronger than this is true. Moreover, in all of these instances, this principle is witnessed by a closed color. Okay, you might be wondering if this principle actually ever fails in interesting ways, though. And the answer is yes. So this first proposition is just saying that if you have large cardinals lying around, then you have failures of these. This first is almost by definition. If kappa is weakly compact, then any non-trivial instance of this property fails, right? Because you have large homogeneous sets for the coloring, right? So if kappa is weakly compact, then u kappa 2 theta 2 fails for all theta. Okay. As successors of singulars, if you're the successor of a singular of strongly compact cardinals, then any instance of this property that can fail essentially does, right? So u lambda plus 2 theta trophonality of lambda plus fails. For all regular theta, well, we already saw that it holds if theta equals the trophonality of lambda. But if theta is anything else, then it fails. We can also have sort of consistency results where we start with large cardinals and get interesting failures of these at sort of non-large cardinals. So the first result in this direction, suppose kappa is weakly compact. There's a forcing extension in which this property, u kappa kappa omega omega fails, but kappa is not weakly compact. We can also be sort of targeted in our approach. For any fixed regular cardinal theta less than kappa, there's some forcing extension in which there are no strongly unbounded functions from kappa squared to theta. Or sorry, other way around. There are strongly unbounded colorings from kappa to theta, but not from kappa to theta prime for any other theta prime. Right? So the principle holds for theta, but fails for all regular theta prime different from theta. All right, what about successors of singulars? We naturally get non-trivial failures even down in aleph omega plus 1. So if there's a super compact cardinal, there's a forcing extension in which we get every failure we could get at aleph omega plus 1. So u aleph omega plus 1 to aleph k, aleph 1 fails for all k greater than or equal to 1. Right? We cannot get this for aleph 0, as we saw from the previous slide, but for all the others, we get this failure. All right. Okay, so I want to move on to a different chapter that at first glance is going to appear maybe unrelated to what I've just been talking about, but which we'll see in what I think is a sort of interesting way, is quite intimately connected. And I want to start by remembering a really nice characterization of weak compactness that's due to Djordjevic. So I want to recall the following definition. A C sequence over kappa is a sequence C alpha for alpha less than kappa, such that C alpha is just a club in alpha for all alpha. All right, so for every limit alpha in kappa, C alpha is a club in alpha. And we won't need this today really, but just for completeness, C alpha plus 1 is just singleton alpha for all alpha. All right, but for today, we really only care about the limit alpha. All right. Now there's a really nice result of Stevo characterizing weak compact cardinals, and it's the following. For every regular uncountable cardinal kappa, the following are equivalent. Kappa is weakly compact. And secondly, every C sequence over kappa is trivial in the following sense. For every C sequence, C alpha for alpha less than kappa, there is some unbounded subset of kappa such that for every alpha less than kappa, there's beta less than kappa for which D intersect alpha is equal to C beta intersect alpha. So in other words, we have this unbounded, and in this case it has to be a club, subset of kappa, D, such that every initial segment of D is already an initial segment of one of these C alphas. Okay. So I think that's a really nice and quite non-trivial characterization of weak compactness. But motivated by this characterization, we introduce the notion of the C-sequence number of a cardinal, which we denote by chi of kappa, which can be seen in a certain sense as measuring how far away kappa is from being weakly compact. So the definition is the following. For every regular uncountable cardinal kappa, okay, if kappa is weakly compact, we just let chi of kappa be 0. And for a non-weakly compact cardinal, sort of the smaller the C-sequence number is, in a sense, the closer kappa is to be weakly compact, in the following sense. Otherwise, if kappa is not weakly compact, chi of kappa is the least cardinal chi, such that for every C-sequence C alpha for alpha less than kappa, there's an unbounded subset D of kappa, such that, okay, well, kappa is not weakly compact, so we cannot hope that every initial segment of D is equal to some initial segment of one of these C alphas. What we get is every initial segment of D is covered by the union of at most chi many elements of our C sequence. So more formally, there is some unbounded set D such that for every alpha less than kappa, there's a subset of kappa B of size chi, for which D intersect alpha is a subset of the union over beta and B of C beta. There are a lot of sort of quantifiers going on here, but all this is saying is every initial segment of D is covered by a small number of elements of your C sequence. All right. So what are some basic facts about this? So first of all, sort of obviously, chi of kappa is at most kappa, right? You know, you can have some unbounded set and just for each element of the unbounded set, choose a different beta that such that C beta contains it. Also not hard to show, but a little bit more non-trivial. At successor cardinals, this C sequence number is bounded between the cofinality of the predecessor and the predecessor. So for every infinite cardinal lambda, cofinality of lambda is less than or equal to the C sequence number of lambda plus, which is less than or equal to lambda. This upper bound is the same argument as in 1. For the lower bound, if you just take a C sequence, C alpha, alpha less than lambda plus, such that the order type of C alpha is the cofinality of alpha for all alpha, this will witness that cofinality of lambda is a lower bound here, right? For any unbounded subset of lambda plus, just take some initial segment of large enough order type. It can't be covered by fewer than cofinality of lambda, many of these, right? Their order types are just too small. In particular, if lambda is regular, then chi of lambda plus is just lambda. So again, as with the U property, we know everything there really is to know about this at successors of regulars. It's as large as possible. Okay, it's possible for it to be small though, right? If lambda is a singular limit of strongly compact cardinals, then chi of lambda plus is as small as possible. It's cofinality of lambda. Okay, what else can we say? The only possible finite values for chi of kappa are 0 and 1. If chi of kappa is greater than 1, if you need more than one club to cover each initial segment, then you need infinitely many. If chi of kappa is 1, then kappa is quite large. It's greatly malo. If chi of kappa is smaller than its maximum, then we have stationary reflection, right? So every stationary subset of kappa that consists of ordinals of cofinality greater than chi of kappa reflects, right? If chi of kappa is as large as possible, there are no such ordinals, right? But if chi of kappa is less than its maximum, then there are stationary subsets of this set, and you have non-trivial instances of stationary reflection. Okay, and also square principles basically force chi of kappa to be large. All right. I'm not going to define this. If you know what it is, great. If not, it's some mean of square of kappa. But if square of kappa less than mu holds, then chi of kappa is infinite. If square of kappa less than omega holds, this just follows from square of kappa, then chi of kappa is as large as possible. What does as large as possible means? It means chi of kappa is the sup of kappa intersect regular cardinals. All right. So none of these are very hard to prove. They're all sort of good exercises to think about. But I want to prove some results showing that a lot of the results here showed that in many instances, chi of kappa is as large as it could be. Can we get non-trivial instances where chi of kappa is quite small? Well, yeah. So suppose kappa is weight theta packed. And there's a forcing extension in which chi of kappa is 1. And for every infinite regular theta less than kappa, there's a forcing extension. These are both cardinal preserving forcing extensions, in which chi of kappa is exactly theta. So we can be very precise about what we make chi of kappa. We can make chi of aleph omega plus 1 be quite small as well. If there's a supercompact cardinal, and there's a forcing extension in which aleph omega plus 1 is aleph 0. All right. Now, you might look at this theorem and say, well, at least in structure, this looks very similar to the consistency result that you presented in the previous section, right? About the u kappa mu theta chi. And there's a reason for this, right? They're really the same theorem, right? So here, just for convenience, was that theorem about u. And the models witnessing these theorems are the same. So the model witnessing, or the forcing extension in which chi of kappa is 1 is the same as the forcing extension in which u kappa kappa omega fails, but kappa is not legally compact. The forcing extension in which chi of kappa is theta is the same as the forcing extension in which u kappa kappa theta chi holds, but it fails for any other value of theta. And the forcing extension in which chi of aleph omega plus 1 is aleph 0 is the same as that in which all of these U principles fail. So this suggests that there might be a sort of non-trivial connection between these two different topics, and that is in fact the case. So I want to present some results in that direction. A lot here remains unknown still. There are a lot of open questions. So first, in one direction, suppose we have ordinals with this, or cardinals with this arrangement. So infinite cardinals, chi less than or equal to theta less than kappa, theta is regular. Kappa is also regular. Suppose there's a closed witness to this U principle, U kappa 2 theta chi. Then the C sequence number of kappa is at least chi. This is sort of the reason that we called this chi of kappa, because it seems to have an affinity for the fourth coordinate of our U principle. Right? So here we're going from closed witnesses to U to complicated C sequences. What about in the other direction? Well, it turns out that there always is a closed witness to U kappa kappa omega chi of kappa. This is just Stevo's number of steps function, right? Take a C sequence that witnesses the value of chi of kappa, do walks and ordinals on it, and the number of steps function witnesses this unboundedness property. There's also a closed witness to U kappa kappa chi of kappa, right? So we always have strongly unbounded functions into omega and into chi of kappa, at least as long as chi of kappa is infinite. Notice that if chi of kappa is 1, then this is trivial, because there's no interesting instance of this if chi of kappa is 1. Also, on a sort of more local level, we have the following. For any infinite regular cardinals theta less than kappa, the following are equivalent. So first, there is some C sequence C over kappa, such that chi of C is theta. I didn't define this, but this is like the definition for the C sequence number, but just applied to this C sequence C. So this is the minimal cardinal chi, such that there's an unbounded set D in kappa, each of whose initial segments is covered by chi many elements of C. So if there is some C sequence C over kappa, such that chi of C is theta, then there's a closed witness to U kappa kappa theta theta, strongly unbounded function from kappa squared to theta, and vice versa. Okay. So before I move on to the last section of this talk, I want to mention some conjectures that remain open. Here's one sort of wild conjecture. I don't know if I actually expect this to be true, but for all we know, it's true that for all regular theta less than kappa, U kappa kappa theta kappa chi holds. Possibly a more realistic conjecture is that this is true, but just for all regular theta less than or equal to chi of kappa. Another conjecture is that the following are equivalent for regular uncountable kappa. Chi of kappa is less than or equal to 1, and the kappa-Trinaster property is Aleph 0 productive. And finally, conjecture the following are equivalent. Kappa is weakly compact. Every reasonable instance of this U property fails. U kappa 2 theta 2 fails for all infinite regular theta. And just the principal into Aleph 0 fails. U kappa 2 Aleph 0 2 fails. Right, so I think all of these are very interesting questions that I have no real idea about. Okay, so in the last about 15 minutes of the talk, I want to talk about unbounded colorings that satisfy additional properties, in particular subadditivity. And subadditivity is a very useful property that has a lot of applications. So let's recall this definition. We say that a coloring C from kappa squared to theta is said to be subadditive if it satisfies two instances of a strong triangle inequality. So for all triples of ordinals alpha less than beta less than gamma, sorry, this should be less than kappa. It's going to have this mistake every time I refresh the slide, but this should always just be kappa. C of alpha gamma is less than or equal to the max of the other two, C alpha beta, C beta gamma. C alpha beta is less than or equal to the max of the other two, C alpha gamma, C beta gamma. There's a third possibility. It turns out that it's sort of too strong and not as interesting as these two. These are the two that you want. So if a coloring satisfies both of these for all triples, it's said to be subadditive. We sometimes care about just one. We say it's subadditive of the first kind if it satisfies one, subadditive of the second if it satisfies two. So these subadditive witnesses to these U principles are often particularly useful in applications. So we often care about when such subadditive witnesses exist. And probably the most useful result in this direction is the following. If square of kappa holds, then we have all of these principles being witnessed by subadditive colorings. So if square of kappa holds, then for every regular cardinal theta less than kappa, there's a subadditive witness to U kappa kappa theta chi for all chi. Right. We actually need something weaker than this, but just for sake of coherence of this talk, I'll just leave it at this. So in particular, if we have any failure of existence of subadditive witnesses to these principles, then kappa is weakly compact in L, so it has large cardinal strength. However, these subadditive witnesses do not necessarily exist, even if the principle holds, right? For instance, remember that if kappa is the successor of a regular cardinal, then all these instances hold. But it's possible that we don't have subadditive witnesses. For example, here's a theorem. If the p-ideal dichotomy holds, then for every regular kappa greater than Aleph 1, there's no subadditive witness to U kappa 2 Aleph 0 2. Right? And this is a principle that we conjecture actually holds for every kappa that's not weakly compact, right? Just this principle U holds at every successor of regular, successor of singular and countable trophonality, right? But if PID holds, then there's no subadditive witness to it. Also a theorem independently due to Asaf Shani and myself. Relative to large cardinals, there are consistently regular cardinals kappa for which square kappa 2 holds, so just a very slight weakening of square kappa. But for every regular theta less than kappa, there are no subadditive witnesses to U kappa 2 theta 2. And this is a little bit vague, but in this theorem, kappa can be arranged to be whatever you want, really. Successor of a regular, successor of a singular, inaccessible. It can be aleph 2, aleph meta plus 1, whatever, right? So even a relatively strong incompactness principle is not enough to give you subadditive witnesses to this U. Right? Square kappa is enough, square kappa 2 is not. All right. So what is this useful for? This has a lot of applications. I want to end by just presenting one. And this is an application to questions about the tightness of G delta modifications of topological spaces. So I want to recall some definitions. So let X be a topological space. The tightness of X, noted T of X, is the least cardinal kappa, such that whenever T is a subset of X and X is in the closure of T, there's a subset of T of size at most kappa, such that X is still in the closure of that subset. We say that X is Fréchet, or sometimes called Fréchet-Urysohn, if whenever T is a subset of X and X is in the closure of T, there's a sequence from T that converges to X. Right? Note that a Fréchet space has tightness at most aleph 0. Right? Being Fréchet and having countable tightness are both very natural weakenings of being first countable, and that's partly why these are interesting properties that a lot of people study. All right. And finally, the G delta modification of the space X, denoted X delta, is the space with the same underlying set whose topology is generated by the G delta subsets of X, right? So the basis is just the G delta sets of X. So a lot of recent work has been done studying the relationship between the tightness of X and the tightness of its G delta modification. In particular, there's interest in whether there's an upper bound on T of X delta if X is some countably tight or Fréchet or even stronger space. Right? So some recent results in this direction. First, a result of these 5 authors from 2019. If there's a non-reflecting stationary subset of kappa consisting of troph-omega ordinals, then there's even a Fréchet space X, is certainly a countably tight space, such that the tightness of X delta is kappa. So in L, for instance, there are countably tight spaces whose G delta modifications have arbitrarily large tightness. On the other hand, a strongly compact cardinal is an upper bound for this tightness. If lambda is strongly compact and the tightness of X is less than lambda, and the tightness of X delta is less than or equal to lambda. Some recent work of Chen Mertens and Septitsky. If square of kappa holds, then there's a Fréchet space X, such that T of X delta is kappa. They can also arrange for this to be alpha 1. Alpha 1 means if you have countably many sequences converging to the same point, then there's a single sequence converging to the same point that contains all those countably many sequences mod finite. If you examine their proof, what they really prove is this. If there's a subadditive witness to U kappa 2 aleph 0 2, then there's a Fréchet alpha 1 space X, such that T of X delta is kappa. Right? And of course, this follows from square, as we said on our previous slide. And there's a sort of partial converse to this. If PID holds and X is a Fréchet alpha 1 space, then in fact the tightness of X delta is at most aleph 1. Right? It could be aleph 1. It's easy to make examples of that, but it's at most aleph 1. Right? So there's this whole sort of constellation of interconnected results here. I want to end with a result that's a sort of modification of this that I think is quite interesting and a little bit different, but also fits into this whole story. And the result is we can actually get a space X like this from a failure of the singular cardinals hypothesis. So here's the theorem. The proof is actually quite similar to this theorem of Chen-Martin's substituency. Suppose that mu is a singular cardinal of countable trophonality, and suppose that SCH fails at mu. For us, let's say that mu is strong limit, and mu to the L of 0 is greater than mu plus. Then there's a Frichet alpha 1 space X, such that the tightness of X delta is mu plus. Right? So we again have this large gap between the tightness of X and the tightness of X delta. All right. So I want to end by just sketching a proof of this theorem. And we're going to need the following folklore lemma. So we've seen that some additive witnesses to this principle U mu plus 2 troph mu 2 don't necessarily exist. But they do exist if you only require subadditivity of the first kind. And in fact, you can find very strong such witnesses. So this is a lemma. It's folklore, not stated in this way before, but really it is this. For every infinite cardinal mu, there's a witness C to U mu plus 2 troph mu 2, such that C is subadditive of the first kind, meaning remember C of alpha gamma less than or equal to C of alpha beta and C of beta gamma, where alpha less than beta less than gamma. And moreover, C is locally small in the sense that all of these sets, dC less than or equal to I of beta, have size strictly less than mu. So if you fix a beta and an I and look at the alpha below beta such that C alpha beta is less than I, there are fewer than mu many of them. Okay, so how do we use this in this proof? So let's fix the coloring C as in the lemma. It goes from mu squared, from mu plus squared to omega. The underlying set of our space is going to be the ordinals below mu plus together with some point on top, which I'm going to call infinity. Every element of mu plus is isolated in X, so the real action is all just at infinity. And the basic open neighborhoods of infinity in X are of the form ni beta, which are, put infinity in, but what else do you take? You take everything in mu plus, except you subtract dC less than or equal to I of beta. Right? So I have, infinity up here. I have mu plus. To form ni beta, I fix my beta. Let's say that this yellow is dC less than or equal to I beta. Then everything else, everything below mu plus outside of this set is ni beta. All right. In particular, it's co-bounded in mu plus. All right. Another way of saying this, of course, is that the closed subsets of mu plus are precisely these sets dC less than or equal to I of beta, or intersections thereof. The fact that this really is a neighborhood base for a topology follows from the subadditivity of the first kind of C. Again, another way of saying this is that if T is a subset of mu plus, then infinity is in the closure of T precisely if T is not covered by any of these dC less than or equal to I of betas. So infinity is in closure of T if and only if there does not exist a pair I beta such that T is contained in dC less than or equal to I of beta. All right, so I claim that this works. I want to very quickly try to sketch the proof of this. First, let's prove that this is a Frichet space. To do this, space is consider infinity, right? So suppose that T is a subset of mu plus and infinity is in the closure of T. We have to find a sequence from T converging to infinity. Suppose first that the size of T is less than mu. Now, for each beta greater than T, for each beta above T, we can define a function f beta from t to omega just by f beta of alpha is c of alpha beta. Now, how many possibilities for f beta are there? Well, mu is strong limit, tsi is less than mu, so there are fewer than mu many possibilities for f beta. So there's an unbounded set A and a single function f from t to omega, such that f beta is f for all beta in A. All right. Now, because infinity is in the closure of t is not contained in any of the sets d less than or equal to I of beta. So in particular, for each I less than omega, we can fix an alpha I in t such that f of alpha I is at least I. And I claim that this sequence alpha I for alpha less than omega converges to infinity. And in fact, because f beta equals f for cofinally many beta, and by the subadditivity of C, this implies that every set of this form only contains finitely many of these alpha i's. As a result, the sequence converges to infinity. Okay. I know that was a little quick, but that's the general idea. If, on the other hand, t has size at least mu, then what do we have? So for each I beta, the size of dc less than or equal to I of beta is less than mu. This was local smallness. So the number of countable subsets of this set is less than mu by the strong limitness of mu. Therefore, there are only mu plus many sets of this form. So the number of elements of t to the L of 0 that are contained in one of these is at most mu plus. But by the failure of SCH, there are more than mu plus many countable subsets of t. So we can find one that's not contained in any of the dc less than or equal to I of betas. Okay. But now we can just appeal to the previous case because we have a subset of t of countable size converging to infinity. All right. And just in the last minute, I want to say why the tightness of the G delta modification is mu plus. So first of all, as we saw, in X, every closed subset of mu plus is bounded in mu plus. This remains true in X delta, right? Every closed subset of mu plus in X delta is contained in a countable union of closed subsets of mu plus in X. Mu plus is regular, right? So again, every closed subset of mu plus in X delta is bounded in mu plus. As a result, infinity is in the closure of mu plus in X delta. However, for every beta less than mu plus, just by definition, beta is the union of d less than or equal to I of beta, where I ranges over omega. Each of these d betas is closed in X, so their union is closed in X delta. So beta is closed in X delta. Therefore, infinity is not the closure of any bounded subset of mu plus in X delta. So no subset of mu plus of size less than mu plus has infinity as closure. So the tightness of X delta is mu plus. And that finishes the proof. I'm not going to prove that this space is alpha 1. It's similar to the proof that is for Shea. Right? So we have this sort of counterexample space X. Okay, so that's all I wanted to say today. I just want to finally point out the artwork you saw on the slides, all due to Vera Molnar, who I recently found out about. It's very excellent. And thank you very much for your attention.
Okay, thank you very much. So, do you have any questions?
I have like a dumb question.
Oh, no, that's okay.
Okay. The chi. How can chi be like 0 or 1 if it has that bound for successors of regular cardinals? Like the lower bound was cofinality lambda for.
Right. So chi of lambda plus is greater than or equal to cofinality of lambda.
Yeah.
This is just for successor cardinals, right? So
Yeah.
if chi of lambda is 0 or 1, then lambda is inaccessible.
So successors can't ever be inaccessible or weakly compact or.
Yeah, inaccessible means limit.
Oh
by
yeah, yeah,
definition.
oh yeah,
Right.
that's true.
Yeah,
Okay.
so
Okay, that's
so this
just
result
for,
doesn't
just for
apply in this
success.
situation.
Okay,
'cause-
I
yeah.
see. Okay, thanks. Yeah.
Yep.
Any other questions, comments? Oh, so Kare. So Kare.
Yeah. Returning to the question at the beginning, because productivity of cluster property is just a question about posets. Can you reformulate the things in terms of generic extension and say something about it, or it's not so relevant about it?
I'm not sure. I think that it probably would have implications for talking about specific forcing posets, but I don't. Yeah, I don't really know of a reformulation of the general statement in terms of forcing extensions.
How about other variations of CCC capacitiness? And there are many different versions. Can you analyze also this productivity of these things in terms of your method?
Yeah, so I stated our result in terms of kappa-Trinaster. It really gives you a pre-caliber kappa. There's also this notion of being kappa stationarily layered. This is a strengthening of Trinasterness. We actually get failures of productivity of this from subadditive colorings. So if there exists, say, a subadditive witness to, let's just say in the simplest case, U kappa, I don't know, LF0, something like this. Then there exists kappa stationarily layered posets pi for I less than omega, whose product again is not even kappa CC.
Sounds great.
Yeah. So these are two that
so you
are interesting that we have about.
This notion. Yeah. Good. Thank you.
Okay. So any other questions? Okay, seems so. Okay. Okay, so thanks, speaker again.